Hello, everyone. Can you hear me? Can you hear me? I'm not sure what's going on. Okay, you can hear me now, right? Okay, cool. Thanks, everyone. Good evening. Um, Thanks for joining us for the last section tonight, and this is our last week for lectures. Um, I know it's not been easy for all of you. There's been a lot of things to learn in these 7 weeks or 8 weeks of going through Python programming, data analytics, and machine learning. Tonight or this evening, we'll be looking at machine learning for classification and a bit of AstroML. We had our first lecture in the morning, which centered on classification in machine learning and also dimensionality reduction. It shared the classification in machine learning, and then dimensionality reduction was done by Najam, while Priya handled the other machine learning and data analytics from AstroML. So just a quick recap for those who are joining this evening who didn't join, I don't know who didn't join last week. Your, I believe by now you have received an email providing the link for your project submission. We advise that all writings should be in Google Colab, and then you only share the link with us. Okay, let's get started. So last week we talked about machine learning. We talked about regression problems, different types of machine learning. And we did a demo on doing regression with astronomical data set. And today we'll be looking at classification. And the good thing about today's one is that we'll be looking at how to collect data from data archives and then using the same data to do machine learning. So I'm quickly going to show you this notebook, which has been shared with you in the week 7 report. It is there already in the folder. So there's no new thing. Everything is there. So looking at this, in week 4, we did um, astronomical data sources, how to handle data, astronomical data in astronomy, how to query data from Visia, and how to use Astro Query. So, well, that's good. So let's quickly look at this. Again, last week we did regression analysis using STSS dataset, which comprises the photometric measurements from STSS. We are going to use the same SDSS data today, but this time around we are going to do classification because that is what we're interested in. Here is how we got this data set. The data sets have been provisioned for you already. Look at it here. It's already provisioned for you in the GitHub repo. But this is just a rundown of how the data was collected. Where did we pick up this data? This data is available on Visia. If you click this link, it takes us directly to Visia. And then it tells us that this is Sloan Digital Sky Survey Release 16. This was published in 2020. This is the link that takes you to the paper, original publication. And then this is a quick abstract telling you about the data set itself. And if we want to see the columns, if you come to this thing here, Visia here, you will see the columns. So you can see that this data set do have a lot of columns. But however, we are interested in a few number of the columns, which we think are very crucial. What are these columns? The object ID, the coordinates, the type of object, the photometric information, which you have here, the AB magnitude photometric information. And then we're also interested in the redshift. We're interested in the photometric redshift, which we collected here, and then as well as the object type, spectral class information. Look at it here. It said spectroscopic class. So this class, it tells you whether the source you're looking at is a galaxy, whether it is a quasi-stellar object, and then whether it is a star. For some of you who may not have background in astronomy, this is quite unique. For majority of the objects you can detect, they are usually, especially for compact objects, they're usually in the form of stars, galaxies, or QSOs or AGNs. But the thing is that these first two are extragalactic origin, whereas majority of the time the stars are within the galaxy. So enough of this. So coming back to the data set itself. Like I said, for you to do your machine learning, to have a background in the data set, you need to also have some domain knowledge, context of why, or the kind of analysis that you want to do. So barely looking at the column I just shared, we have selected the columns that we're interested in. We write our query, import VZR from Astro Query, import the VStack from table. The reason why we are doing this is that we're going to do multiple queries. And then we decide the number of limits. So that data set is very, very huge. Please don't try to download all of it. Otherwise, your system is going to crash. It's very, very big. So the best thing to do is to use row limits. Row limits is you can increment it. You can also reduce it depending on the size of your machine or memory. In this case, we restricted it to 150,000 data points for each of the classes that we're interested in. So we define this, initialize the VZR function, class, sorry, and then proceeded in applying constraints in the spectral class. We selected for galaxy, QSOs, and stars. And then for each of these query, when it's done with them, we concatenate it into, we stack it, yeah, more like vertical stack it. We stack them together. And then when we do this, we don't have this 450,000 rows. So you can see the first few, I guess the first 10 and the last 10 or so data sets. And we save our data in CSV file. Now this data has been saved. You can find it here. SDS SDR16 class c.csv. This was also run this morning. It's there in the GitHub repo. So you might choose not to. If you want to play around, you can also play around. But I decided to just show you how you can go from taking data from the archives and doing machine learning. You know, most times when some people, I guess some of you who have done something before, you probably will see some nicely data somewhere, but like if you go to Kaggle, some other data set, you might not see astronomical data set there, or you might see a few, but they are not so common. So you can actually just utilize the data we have in VCR to do this analysis. Okay, moving forward, this is addressed. We'll come to the classification. Machine learning is of three types anyway. Machine learning is a component of artificial intelligence. And we can have things like deep learning, machine learning, and then machine learning itself. We also have what we call supervised learning, unsupervised learning, and reinforcement learning. This thing we explained last week. We also proceeded to talk about a bit of the differences in this. For supervised learning, we have the regression problem, we have the classification problem. So the regression problem was addressed last week. A bit of the classification problem was also talked about. I know in one of Najam's hands-on presentation, he did talk about, I think, some simulated exercises on doing classification and regression. So this text here is quite similar to what we had last week. A majority of the time, we keep collecting data, we analyze this data, but we want to see how we can use the previous data that we have to do predictions that we can use to now to create models that we can use to now predict new observations. We are in the era of LSST, right? Now imagine you you are getting data set from LSST, and then maybe you're finding, you cross-match it with SDSS, you are finding the same source, and you're still like, okay, what do we have? You can just say, oh, where they have previous data, let's use this data to train some machine learning models that we can use to predict this kind of object. What is it? What spectral type is it? What is its origin? Is it galactic or extragalactic? So these are some of the things that we're looking at. So this is not so deep or complex. We're only going to restrict ourselves in using the photometric information from this observation. We're not even using the spectral information. I believe I challenge you maybe to see if you can also look for how to get spectral information from SDSS and maybe use it to do some machine learning task. So we are looking at the properties we're interested in is the magnitudes, right? Priya has mentioned, has explained what magnitude is in astronomy. The magnitudes, the colors, which we have here. So this is what we're interested in. Now, how are we going to go about this? We simply just go take our data sets, right? But first and foremost, we import the tools or the functions that we need, most especially NumPy for maybe loading data if need be, pandas for loading data, of course, doing plotting. These two are for plotting. Every other thing here is for machine learning related. Okay. Standard scaler for scaling our trained data sets, label encoding for transforming our labels or classes into numerical values. Cross-validation score, these are tools that we're going to use for doing these other ones are for metrics. How do we evaluate this classification? And then these are the set of estimators, classifier estimators we're going to use to do our machine learning. Now let's get started. Let's load our data set. This is not new. I'm very sure some of you are already doing this. This is the data set, you can see this is the first 5 column rows of the data set. You see it's very clean data, object ID. Now the object ID is very useful if you're interested. Maybe if you see some properties that you're interested in, you can simply just go ahead, take this ID and maybe query other information that you are interested in the archives. This is the right ascension and declination tells you, okay, this is the right ascension, or more like the longitude and latitude if you are talking about maybe Cartesian coordinates. Well, this is equatorial coordinates. So in astronomy, we do have multiple types of coordinates. Ecliptic, we have equatorial, and then we also have galactic. Now, this class information is the class property, whether the source is a star or a galaxy. So that's how it's defined. So I think 3 is for galaxy and 6 is for star. If my brain is not. Yeah, I think that's how it's defined here. Yes, 3 is for galaxy, 6 is for star. So you can see it does follow the same information here. 3, whenever you see 3 here, it's a galaxy. And then the photometric information, this is, I think this is around the time the observation was performed with SDSS. And then this is the column that we're interested in. This is the column, this is what we want to do. We know this is done already, but we want to do, this will only give us binary classification. We want to try multiple classification. What it means is, in classification, we do have 2 types of classification. We do have binary classification. We also have multi-class classification. What is multi-class classification? Multi-class classification is a case where you have more than 2 classes in your data set. So you want to say predict maybe 2, 3, 4 classes in your data set. Okay, moving forward. A bit of the thing that you should do whenever you're doing machine learning tasks is when you load the data, you don't just jump in and go and start training immediately. No, you need to inspect your data. It's very useful, though this data is relatively clean, so there's not a lot of things that you need to do. But there are cases where the data can be very, very messy. It means that you need to do a bit of maybe dropping a lot of data sets. It could also be doing some imputation. It could also be doing some transformation, or even filling missing informations. You understand, just to make sure your data is ideal in such a way that it can be useful to you. So, okay. And then what we do is we check the number of shape. I usually do this. Shape will tell you the size of the data set, how many rows and how many columns. This is a good way to start. Then the next thing to do is to use the info function. The info function just tells you the information about your data set. It tells you that this is a pandas data frame. Your data is of pandas data frame, and there are 450,000 entries, and there are 13 columns, and then it goes ahead to tell you, list out the columns for you, tell you how many number of, if there are missing values, it will tell you, or this is showing here non-null. Non-null means these are the all information is complete. There is no missing value. It also tells you the data type. So you can see a lot of that in these 13 columns. Majority of them are float type. The first thing we did the first week was to talk about data types in Python. So you can see this is mostly float type, and then we have 2 integer types, and then we have 2 object type, right? So we don't need a lot of work in this cleaning in this data set. But because we're interested in selecting only data sets that have redshift information, if you look at the redshift here, you will see there are only 162,516 rows with redshift information. The others do not have. So what do? We constrain our data sets. So constrain our data sets to only those ones with redshift information. And then when you do that, what do you do again? That is what we have done here. This is constraining the data set to only redshift. So we'll say, please go to the redshift information, select all rows with no null value. You understand? So, and then this is saying not NA means not a number. In the case where usually NA is not a NaN is not a number. Not NA means not a number. So the ones that are not a number, I don't know the right word to use for it, but like this is more like the inverse of it anyway. So this will filter off this. And then at the end of the day, when we run this info again, let me run this. When we run this info again, you can see our data size have reduced. We only have 162,516 entries at this point. And the beautiful thing about this is this data is still enough. We feel it's still enough for us because we're only doing a demo, but you can choose to also, like I said, if you increase the data set, you can play around. So we think this data is still quite enough for us. And for the columns that we're interested in, they all have the same number of rows. It means there is no missing data. And then we have the spectral class, SP class information. So we want to see actually how many, after doing this filtering, how does the column look like? You can see that in this 162,000, roughly 140,000 is galaxies. Close to 13,500, I'll say 13,400 are quasi-stellar objects, and just 8,754 objects are stars. So you can see the star is very little. Now, in this case in machine learning, this is what we call an imbalanced data set. It is always ideal when you're doing classification to go with cases where the data is classes are a bit balanced. So where, say, if you have 2 classes, they are almost of equal, close to range, maybe 40, 50, 30, 70, 40, 60, or even 50, 50. So it can never be ideal, but they should be of close range. But in real life, this is not usually the case. In real life, this is not usually the case. A good example of this kind of problem is all of you use an email. Every day you get email, right? Now, email companies, what they do is that they train machine learning models to do binary classification, whether an incoming email is a spam or not a spam. Why? Because they know that spam irritates their users, their end users. So over time, they have been collecting data. They've seen a couple of cases where people have manually indicated that this is spam, and they have looked at the information of this kind of emails, maybe the kind of title, the text in the image, maybe the email handle itself, email address itself. So these are all of the things that they factor in to create features that can be used to train machine learning model, which is applied in your email. So what it means is that as your email is coming in, it runs the inference and say, this email is a spam or not a spam. But majority of the time, the email that comes to you are not spam. So on few occasions, you encounter a spam. So in this case, if you are to manually collect this data yourself, you are going to see that maybe out of 10,000 emails, or out of 1,000 emails, or out of 100 emails, maybe one or two are spam. Another example is financial transactions, right? Financial transactions, maybe cases of fraud. Fraud is not something, yes, it happened, but it's not like you might run your transaction for years and then you don't get to encounter cases where you're being defrauded. So banks also run things like this where they try to also run inference on your data with the model that they have trained to predict whether a financial transaction, maybe banking transaction, is a fraud or not a fraud. So what it means is that the fraud cases will be very minor, whereas the non-fraud cases will be very high. So these two are examples of imbalanced data sets. You can also find it in many other things, maybe possibly in astronomy. Um, Possibly in astronomy. Maybe you can say radio emitting objects. There are majority of them are going to be galaxies, and then a few of them will be stars, right? And maybe some weirdo kind of objects, maybe cases where you have CVs. CVs are not that many. Maybe you're looking at binary systems. How many of them are CVs? You notice that they are not that many. So in that case, the CVs might be what might consider to be like in that case, if you are doing that kind of problem, you might consider it to be what we call an imbalanced data set. I think I've spent a number of times here, so we need to move forward quickly. So there are a couple of ways to handle this issue of imbalanced data set. A quick search on Google on how to handle imbalanced data set, you will encounter a few examples. Usually the best thing to do is you either do oversampling or undersampling. So this is just statistical terms. So oversampling simply means that you have to look at the minority class and try and resample it by increasing it. So in this case, we have three classes. So if we want to oversample this, what we are going to do is that we'll see how to increment these two classes such that they will be close to the majority class, and then they are now a bit proportionate. On the other hand, you can do undersampling. Undersampling is a case whereby you randomize you randomly select the majority class and select it proportionately to the minority classes. So what it means is that if we are undersampling this case now, we will trash this 140,000 rows to possibly maybe 20,000, such that the differences are no longer that much. There's a tool in Python for doing this. It's called Smote, SMOTE. You can Google about it, but because this is not part of what we are going to talk about today, I'm not going to focus on it. Yeah, so let's move forward. Let's if you remember in the description here, we talked about this transformation. And then I'm going to give you an assignment. The assignment will be that instead of training, after we finish running this training, maybe select only a particular column, maybe 4 or 5 columns, and run your machine learning and see how it's going to look like. So now we proceed. We create new set of data. We've done this last week. So this is color. We are creating the color. Color simply means we are looking at the differences between the magnitude range. So these have 5 magnitudes, the U, G, R, I, and Z magnitude. Now, out of it, we'll create 4 colors. And then now that we create these 4 colors, it's going to be very useful for us. Colors is very essential in astronomy. Sometimes it tells you, depending on the range, it does tell you the demographics, a bit of the demography of the objects that you're dealing with. For stars, which you did, I think, in week 3 and week 4, you will notice that it was the case where you plotted the absolute magnitude of the star and the color. It immediately showed you what we have, what we usually call in astronomy, stellar diagnostic plot, which is the HR diagram, which will tell you whether the star is hot, whether it is cold, whether it is red or blue, whether it is massive or not so massive, or whether they are off the main sequence. Maybe say they are non-main sequence stars, or they have evolved. More evolved means they are no longer lying in the main sequence region. Maybe due to certain properties or behavior or environmental conditions of the star. They've moved up or down the main sequence. But anyway, that is not what we're talking about here, but this is just to highlight what the color means. In astronomy, you can read more about it yourself. So you can see we have incremented the number of columns in our data set, right? But in any case, we are not interested in all of these data columns. We already know the ones that we're interested in, that we want to use for this analysis or modeling. The next thing we do is take the spectroscopic class information. We want to transform it. We want to encode it such that it can be represented as numbers. So if I run this, let me see, I'm not sure. Okay, no. So run this now. So, okay, good. So we use the label encoding from scikit-learn to encode. So instead of manually writing a code to say transform this into galaxies should be 0, blah, 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 1, the other 2, you can just encode it automatically with label encoder in scikit-learn. You initialize it and run the fit transform, and then it does it for you. You can see it here. All galaxies, we created a new column called label. And then all galaxies are now 0. Quasars are now 1, and then stars are now 2. So if you run this, it gives you, and then we run the describe. So the describe in function in pandas, I'm very sure I'm sure you've encountered it before, will quickly navigate through all of your data sets and pick out the numeric ones to now run. So usually the best thing to do is to select the columns yourself and then run the describe. But because this is not like so heavy, we can run this and then automatically select them. We can see object ID is not something that we're interested in. Right ascension and declination will give you an idea of where this object lie in the sky. So you can see that the right ascension are within 5 to 180 degrees in right ascension. The declination is within 0 to 72 degrees in declination. The classes here are a bit it doesn't. This is a case of a uniform value, so you're not going to get any sort of distribution from this. Then this is where we get to see a bit of distribution. The magnitudes are quite continuous, so you will see a bit of, this is the, if I'm correct, this is supposed to be the standard deviation. It's supposed to be the minimum value. Yes, 10.5, and then this is the maximum value. So this is just what it tells you. And then for the colors that we created, you can see we do have cases that have weird colors. But in any case, we're not going to do, if supposedly this is a science work that we need to publish, what we'll do here is to quickly maybe filter off a bit of this, because this might probably be a bit of contamination. You want to make sure you clean up your data as good as possible. So this is the label that we have created. You can see galaxies, they still retain their values. Nothing has changed in terms of the number of items. And then that's it. Then I also emphasize that a good number of times it is also good that you do some visualization. So visualization helps you understand the data in a way that you may not have acknowledged before. So, with that, you already have this code. This is the same code we used last week, so we just reused it. So nothing changed anyway. The only thing that changed is just maybe the name of the magnitude. That's the only thing that changed. So that is the usefulness about using code. So anyway, if we run this, it's going to show us a bit of the distribution for the magnitude, the 5 magnitude, the color. Now you can see in the describe, this thing I was talking about, where we have values that were showing us that we have things like -10 something something. I think you can still see it here. Yeah, this is -9, this is -7, -12, -6. So you can also see it. Can also see it manifesting here in the distribution. So this is the case where there's a whole lot of difference in the color. It's quite weird. So in this kind of situation, the best thing will be to further do inspection, especially if you don't expect that kind of behavior. The best thing will be to further do inspection. But we're not doing a whole lot of the digging right now. This is the redshift. You can see the redshift is a bit, how will I say, trimodal. So you can see, you can basically see that you have more like 3 set of distributions here. And maybe if you are somebody who have studied SDSS for years, or maybe read the paper, you might begin to acknowledge what is happening here. But from a simplistic point of view, what we can say is maybe this is showing us the typical classes that exist. It gives us a clue that maybe there are 3 sets of objects here, and their redshifts are peaking within this region for each of those classes, though there is still a bit of contamination. If you recall, for galaxies, galaxies are supposed to have high redshift anyway. So stars are supposed to have lower redshift. So the chances that what you are seeing here could be majority stars, but there is still a bit of contamination for what the redshifts are. Remember, these things are measurements. Sometimes there might be instrumental error and they might not necessarily do. So this is where you need to also read up more to know what kind of redshift you, maybe where you can even do further exploratory data analysis, which is what I'm expecting you to do in your project, whereby let's say you're working on something like this, you can further inspect the stars and compare their redshift information and say, okay, I'm not expecting this kind of redshift for a star. You can also give your justification. And especially if it's a case whereby maybe the instrument sensitivity will only pick out galaxies at certain redshift. So where these things are modeled before even they start operating. But this is something that you can find in the paper, maybe in the SDSS. So you can basically say that, oh, this is mostly representing concentration of maybe different classes here. Maybe this is, I can confidently say this is galaxy, this is star, this is a bit of maybe galaxy, star, and QSO, or maybe possibly QSO, blah, blah, blah. So yeah, and that's it. So we're not doing a lot of digging here. In this case, we now move to, why do we want to do this machine learning? We want to predict the classes of stars, of the objects. Sorry, not stars. I'm biased because I study stars. Want to see if we can predict whether the source is a galaxy, a quasi-stellar object, QSO, or a star. Now, because of domain knowledge, we're not interested in every other information in the data set. We're only interested in the colors and the magnitude. And we have already encoded the classes itself. So what it means now is we'll select our features and our label. So I did it here such that it could be very simplistic for you to kind of like think about this, you know. So this is more like saying, okay, this is our x's, and then this is our y. So remember the mathematical relation f is a function, y is a function of x. So basically, this is also the same thing that you most times do in machine learning. And what it means is all of these here are independent variables, whereas the label itself is the dependent variable, which is the one that we want to model such that so that we can predict it. So now moving forward, we can now look at the whole distribution for these features. Here we create a heat map. A heat map is no other thing other than showing you how your features behave, where they lie in the correlation space. So that's basically what is going on here. So you're going to see that you're going to have, say, okay, I think I need to extend this to 12 and this 10. Yeah, so sorry. Let me see. Yeah, it does fit in now. It does fit in the screen, so you can see it. So what usually happens is when you do your heat map, I think this has been explained in the previous class. It shows you this is the y-axis and this is the x-axis. So it tries to show you the correlation among all of this. So in this case, this is 1 here. So you have UMAG at the bottom is UMAG. So the correlation of two of the same variable will always give you 1. And then when you do UMAG and GMAG, you're going to see that the correlation is close to 1, 0.81. And what you can see is that as you go down the magnitude range, just keep our eyes up here. You notice that the correlation is dropping. Who can tell me why this correlation is dropping? The reason why it is dropping is because these magnitudes represent filters. And I think these filters are going from blue to red. So this G filter is close to U filter. So the brightness of the changes will not be that different. They'll be close. So the same thing. So as it's going towards the red, they begin to see the difference in the correlation. So this is how I can interpret it as well. You can also see here that, sorry, can you guys hear me? Not sure. I think I'm having, can you hear me?
Yes, sir.
Yes,
Okay.
you are audible, Rana.
Okay, good. Yeah, I was getting like I'm having network problems. Okay, so here, so you can basically see the same. So this can be interpreted by looking at comparing the y and x and looking at how it all behaves. So you can also see the same behavior going downwards here for this case. But this is not well what to concentrate on. So here is just telling you, okay, the blue ones they are not correlated, they are inversely correlated. And then the yellowish are a bit more super correlated, the bit of the red. Sorry, I'm very terrible in colors. So, but you can see the values yourself because the values too have been indicated in the plot. So now what we do is we move forward again to now proceed into selecting our X, which is our features, and our Y, which is the class that we want to predict. If you look at this, if you look at this cell here, you're going to see that this is your X, and this is the Y. So we have filtered it from this, sliced it from the data itself. So this is how you slice data. You slice the X and you slice the Y. Then after doing so, we will use the train test splits. I explained the train test splits last week. It is a function for splitting your data sets. It is a function for splitting your data set and also defined to train and test. The test size is usually defined. Most times it's 20% of the data, but the choice is up to you. So it's not a must that you stick with it. So you can choose to do it 50-50, depending on the size of your data set. Okay. Now we've done this, we can now look at our trained data set. So this is the trained data set here. Okay, sorry, I think I need to define this. Yeah. And now here is our trained data sets. We have 100 out of the 162,000. You can see that 130,000 have been selected as trained data sets. And the remaining, I guess, 30,000 as well will now be 32,000. It will now be the test data set. Then here, we simply run a set of pipeline to evaluate our model. What it does is that it takes a model you have trained, the name, this is a function anyway, your trained data set, your test, your train features, your train labels. Feature names is optional. The reason why it is optional is because we've already selected the features previously, so we're not loading all of the data sets. We've done that already. This is cross validation of 5, means we want the thing to run for like up to 5 times or so before giving us the real value. Here we are using the pipeline function. The pipeline function is a way of encoding some of the functions that we want to apply with in our training process. So we say, oh, pipeline, please, we need a scalar. What we need to do is that, oh, the scalar is going to just normalize our training data sets. And the CLF classifier is the model. Now this pipeline will now be applied somewhere here. We'll get to that later. Let's try it. Let me finish explaining this. So the cross-validation predict will now kickstart the process of taking your pipeline, running this pipeline here, calling these functions, and applying it to the data set, and taking the model itself and fitting. Your method is to predict, and then this is where it now fits. It fits your training data set. It takes with your training data set anyway, so your features and your labels. And then when it's done doing so, you will now take the predictions and evaluate it with the one provided from the model and do the same thing. So accuracy score, precision score, recall score, and F1 score are the evaluation methods that we use for classification. Just like last week, we talked about the root mean square error. We talked about the mean absolute error, right? We talked about the arrow square, R2 square. Yeah, the R2 score, sorry. Yeah, the R square score. So you need to keep your eye for your evaluating classification. These things were also shared in the PDF files that was shared with you. Precision tells us how well the model is generalizing. For imbalanced, sorry, for imbalanced data sets, accuracy is not usually the best thing. Because I know people say, what is the accuracy? Accuracy is 90%, 50, 100%. But remember, if you say your accuracy is 98%, what it means is that in 100 times, it's going to predict 98 times correctly and 2 times wrongly, right? Good. It sounds cool. But the problem with it is if you are dealing with imbalanced data sets, remember your imbalance in the imbalanced data set, the other class is also very minor. So what it means is that for the two times that it fails to predict, it might actually be that that is also imbalanced data set. It's also not predicting it very well. So precision is a one that is a bit robust. So precision and recall is a bit robust in the sense that it tries to say, okay, for each of the time that it is predicting a class, the class, how accurate is it predicting that class? Both whether it is true or false. So how your true positives and your false true positives and your false negatives. How is the model performing in all of this? So this is generally how this thing does. The F1 is the harmonic function that also calculates the precision and recall case for you, whereby if your model is generalizing very well, then in that case you are going to have a very good F1 score. But remember, all of these things are scaled from 0 to 1. So the closer these values are to 1, the better your model is generalizing. If you have a good accurate score of, say, 98% and your precision is 60%, your model is performing poorly. So keep your eye on your precision, recall, and F1 score for a multi-class classification. All right, so we move. So the classification report basically will also display these informations for you, your precision, recall, accuracy, and the F1 score. So it's not doing anything different. Just like, so I want you to just give me this all of this information in one go instead of just running them one after the other. And then here is just a plot showing you the confusion matrix, who also shows you, which will show you, okay, how well each of these models has performed. So this is basically what this code is doing here. And then the next one is the ROC AUC score plot, which shows you from the normal partition of 50%, the growth of your model. So the growth, if it's close to way above, close to 80, 90, approaching the edge on the top left corner, then it is doing quite well. Anyway, I think the best way to explain this is to, let's see if we can run this. I know this is going to take some time. Okay, it's already run. It is already run here, so I don't need to run it again. So, but if you are running this freshly, it's going to take some time because this is doing one, the data is a bit huge. Not that it is that huge, but the process of iterating over doing your cross validation multiple times will take a couple of time. And in that case, it's going to take time. But in any case, let's look at what it has shown us here. So we are using 5 classification methods. These classifications are already embedded in scikit-learn. If you recall, when I shared this last week, we talked about classification. So if you come to scikit-learn, you're going to see classification, regression, clustering, right? If you go to classification, you're going to see a couple of models here. Maybe let's look at let's look at okay, also so decision tree. So we have classification. So if you come to the classification, you need to import it from tree. So it's a tree type model. And they do usually will have examples. This is just you showing you the depth, how it makes its decision tree. This is something I would actually like you to explore later in your own time to see. Maybe if you run a decision tree, try and plot the tree. It's going to tell you how much depth it is going in terms of how it is able to make the decision and do your classifications for you. Well, that is not what we are going to concentrate ourselves on. I'm just trying to tell you that this is where you can find all of this classification. They are all here. They're also well documented. So don't think it's just something that came out of the blue. You can consult this documentation. You can also do a bit of googling and you see tons of examples. So we've imported random classification, random forest logistic regression. So for regression, in linear models, when you do that linear regression, you also have a way that we can use it to do logistic regression. In that case, what happens is that it uses the loss sigma function, which instead of propagating things into maybe continuous, you kind of like binarize it, like say, okay, oh, positive values represent the other classification, negative values represent the other set of classification. But anyway, that is not what we're going to dwell on now. So called random forest classifier, logistic regression. We're basically just using the default functions right inside these classifiers. We are not maybe doing a particular thing for the parameters. We are just using the default parameters. The only thing that is changed here is that in this case, this is random states. It's just for us to, there are a couple of them that supports randomization states where you have to like try to make it reproducible such that whenever someone else runs it, they should be able to get the exact same value in decimal points. You understand? So that's it. So we run these models, and then a Fabric pipeline will take this model and start training them. The first one is random forest. That's the model name. You can see for random forest, had an accuracy of 0.8619. The precision is 0.83. You can see the precision is very close to the accuracy. Recall is also very close to accuracy. In short, the recall and the accuracy is almost the same. It's the same actually. So it means the model will definitely do well because there's no discrepancy in the values. Then F1 score is a bit is still better than the precision. So it's doing quite well. And then this is the classification. This is the classification report. The classification report now tells you for each of the classes. So you can see we have 3 classes, right? 0 for galaxies, 1 for QSOs, and 2 for stars. It gives you, this is where it is now telling you specifically for each of the classes how it performed in the testing. And for galaxies, 89% of the time it does predict galaxies accurately. For QSOs, it performed poorly for QSOs. For stars, to a great extent, it did well, but it wasn't that great compared to galaxies. So you can see that this model is biased. This model will predict galaxies way better than it will predict the other classes. And you can tell why, because like we say, this is an imbalanced data set, right? But notwithstanding, this is just more like an experiment. And then this is the confusion matrix. Now you can see the confusion matrix here. You can see the whole zeros, 1, and predicted. So this is the actual value, and then this is the predicted one. And then it does quite well for galaxies. You can see galaxies are way too high anyway. That's why I say it's very, very imbalanced. It does quite well for galaxies, but the other ones are also not so great. And then for 3 type models, there's one feature the models usually have when you're done training. It has this feature called feature importance. The property called feature importance. Feature importance is telling you how much contribution the features made to the data set. Now, from here, you can see that the first 5 columns are quite great compared to the last 5 columns. So these are some of the things that you can do initially before you train your model. Or because let's say you are doing a project now, a scientific project, this is not where you're going to stop. You need to also experiment a lot to now figure out the parameters to that features, the ideal features that will work in your case. the parameters that will also work, that will be ideal for your case. And then the reason is because you need to create a model that is, train a model that is robust, that can do your predictions efficiently. So if I'm to work on this project again, what I need to do is that I'm going to select this first five features. You can see the colors are contributing way better than the magnitude themselves. So you can see, which is also the statement I made in the doc at the beginning there. So you can, this is one experiment I would like you to do. I want you to take this first five features. So what it means in the future, the state there, variable, you remove these five. Just remove the first five and leave these ones. Train this model again and see if it's going to improve. I can assure you it's going to improve. Okay, because this is already a known task. So it's going to improve. So this is the ROC curve for each of the classes. Um, for stars, I think stars is quite okay. So the thing about ROC is that it's telling you the growth. The growth of your ROC curve will tell you how your model will perform generally. If it is around here, then your model, this is the baseline. So it's just like when you do probability, when you say if something is around 0.5, it's not so great, but it needs to be grow above 0.5, close to 1. That is when you begin to say, oh, this is the correlation is quite okay. So if you are scaling your correlation from 0 to 1. Okay. Here, you can see the models here are quite great. The ROC curve is to a great extent good. It's usually curved anyway. So this is where it is comparing the true positive to the false positive. And this is how you visualize how your model is performing. This is also where you begin to talk about explainability, right? Okay, when you compare, you use your model to, you do your prediction, then you compare the whole predictions against the true values, and you begin to say, okay, well, I think my model is learning, or whether it is not learning. So here you can see this. You can see the one for Galaxy is a bit weird. It was growing initially and then just dropped. So it's not really curved in the essence. So it's still not great, that much. So for QSOs, also has its own set of shape, which is quite good, but it's not that great. It's not that great. But what I'm going to suggest, like I said, is try and use the other features, exclude the magnitudes themselves, use the colors and the redshift, and I can assure you you're going to see great improvements. You could also maybe proceed to maybe drop off the cases where you notice some weird redshift or weird colors when you, especially after calculating the colors. You can also, maybe it will lead to great improvement. So for things like logistic regression, it performed poorly compared to random forest. It performed poorly compared to random forest. And you can see it even in the accuracy, in the precision, recall, and F1 score. This is the classification reports. So you can see these values are way lower compared to, yeah, it did well for Galaxy, but it's not generalizing, to be honest, it is not. And this is the confusion metrics. You can also see the values here for each of the classes. It's just about 20% above the baseline. For decision tree, we can see almost similar behavior. Its performance is way lower than the random forest. And you can also see the future importance. You can see the future importance is closely related to that of the random forest. So this is very, very ideal. And this is why people tend to use three methods a lot in machine learning because they are easy to generalize for um, imbalanced data sets. Remember, we did not try to balance our data sets, yet we were able to get reasonable results. You see, the ROC AUC curve is very poor compared to even logistic regression and random forest. For k-nearest neighbor, we are seeing maybe to an extent grades. I try to improve for stars, but it's also not generalizing very well for QSs. And though I don't want to ask question, but one of the reasons why sometimes you will not be able to generalize very well is because of QSOs and galaxies will have similar properties because these are basically center of galaxies. So the properties are almost the same. You see, very weird ROC curve. Yeah, for support vector mention, wanted to look like it was going to do very well. I think it has a better accuracy recall compared to the others. Let's see the ROC curve. Yeah, you can also see. But I think, to be honest, random forest still has a better ROC curve. So this is it for this exercise for classification. And this is a starter. I'm not gonna lie to you. This is a starter. This is not the end of classification in machine learning. If you're interested in machine learning, I'm going to advise you to take a course. You can check out Cargo Learn. They do have a course on machine learning. I think they have for, yeah, they have for machine learning. They do have from even data analytics. You have for machine learning, different types of machine learning. You're going to see it there, and it's free. So it's going to take you through. And what you can also do is that if you have tons of data sets in astronomy that you want to play with, you can also, while you learn there, you're also going to learn more about the hyperparameter tuning, what all of these metrics are all about. I think it's also in the note that have been shared with you. They have been defined there in that note. So just because of time, though I'm not going to explain this, Priya and Najam is not here. In the morning lecture, they talked about principal component analysis. And what I'm going to advise you is to go to YouTube. You go to YouTube, you should search for the breaks astronomy, and then you should be able to see, this is the lecture we had in the morning. So in the second half of the lecture, this is where you can start from the 50th, larger the galaxy, the from the 50th minute. Then instead of taking two different. So pay attention to this. So week 7 machine learning basics for astronomy. You can see, so you can start from the 50th or so minute. That is where we Najem started the whole lecture on it. So you can start there and watch that part of the presentation. The notebook has been shared as well. The notebook is shared here in the dimensionality reduction. So dimensionality reduction is no other thing other than, imagine you have a case where you have a lot of features in your data and you want to reduce, you want to decompose the features. So that is what it's all about. But I'm not going to talk about it because Priya emphasized that we should tell the students to go watch the presentation on YouTube. It's already available on YouTube. Well, apologies about that. They are on their way and they're not able to join us this evening to make the presentation. But while I'm gonna try and show you something. The Astro ML in one of the in Priya's presentation, she did talk about Astro ML. So we have this is a textbook in astronomy called Statistics, Data Mining, and Machine Learning in Astronomy. Let's see. I'm not sure why. Yeah, so this book is free for you to download. But I think they do have a free copy for you to use if you want, or you can buy. I'm not sure. Let me see. Oh, this is Preston page. This is textbook. Yeah, so you can basically just, I think you can go through the textbook right here. User guide. So you can read the textbook online here. Yes, that's actually the best thing to do is to reach. These are each of the chapters. So you can read the textbook. Or please do watch the video. I think Priya did show how to, I think maybe you don't know, I don't know if she was showing the exact copy. I think she has one, but you can also ask the question in the Slack. And they do have series of examples on machine learning and data modeling. So this is we did something like this. We did something similar to this last week, if you recall, where we trained a regression model to predict the redshift of photometric redshift of galaxies using SDSS colors. So we are basically just using the same data set. The only thing is that we've queried this data set ourselves. We didn't use a clean data set that someone has provided. So you just query data set, randomly select yours, and you can start. So they do have a couple of notebooks. They do have series of notebooks that follows the book itself. For those interested in Bayesian statistical analysis, you can find those informations here. This is an example for classification. They have for classification as well. And this is where they try to talk about classification in essence. So this basically is the idea of how the whole metrics of precision, recall, F1 score, or the true positive rate, or the ROC. You can see it here. This is what they try to define it. And they try to run a couple of examples using their own data. And you see, this is the ROC curve. This is their own case. This is for different models that they tried out and the efficiency rates. So these are a couple of things that you can do. I think they also have a GitHub repo that you can check. Let me see. Yeah, there's a GitHub repo. Okay, see Astro ML notebooks. So you can see for each of the chapters, this were just updated some 2 years ago, 3, 4 years ago. If you're following the book, you can go through and then you will see So this is the notebook, the one that was shared with you, the dimensionality reduction. So if you read the book, you can also see a couple of the examples here from the notebook. That's the only way you'll be able to understand this set of analysis being done here. So I wouldn't want to jump into something that's not in my area. You can also just watch the video and you pick up a few things there. So I think I'm going to stop here. We've gone past the range, so I'm open for questions. These informations, I say they are online. You can also get to ask questions in the Slack, and I know Priya and Najam will help you do so. Sorry, I'm only just saying this. And I say, could you close the bottom right Jupyter prompt? Okay, I think that was in the past. So okay, Anjana said, is there any minimum size that the training data set should be? Well, your data should be reasonable enough, but it all depends on the amount of data that you have. The larger the data, the better, but usually we'll probably say at least a few hundreds, starting from a few hundred, but this also depends on the use case. If it's something that there are tons of data already, then why not? The larger your data, the better. You understand? The more robust your model will be able to generalize. So make do of the data that you have. But if it's a case whereby it is so big, like in the STSS, usually what you need to do is to constrain it to something that you think is reasonable. Because you can't process that data on your computer. Even the memory, probably that data is probably in tens of gigabytes, and it's not something that your small RAM or compute can consume. So the best thing will always be to make sure you have reasonable data. Okay, that's the only question I'm seeing here. I don't know if there are other questions. Otherwise, we can call it a day here. Like I see, I think a new question is coming in. Okay. Oh, thank you very much, Anjana. Yeah. So please try as much as possible to do your capstone. I don't know what you're working on. If you're doing strictly data analytics, then I believe you already have enough information to go from A to Z of what you want to work on. And I see a couple of people still asking questions, like whether we're going to do presentation separately. No, you won't do presentation separately. What you need is the same way you have these notebooks prepared like this, you can write text, you can also write your code. And if it's a code, maybe you're doing some analysis, just like in the one I just finished showing you now. Oh, sorry. Here, I've written a bit of the concept, well formatted. So anybody can, even if I don't run this now, I can just download it and show you can read it. The same way if you go to GitHub, you will see it there. Let me see if I can find the GitHub. This can take sometimes. Okay. Yeah. So you can see here, if we come to this notebook, I think this is latest push moments ago. This is a notebook that's been run, right? The text can be read. Anybody can read this. They don't need to run it. You can see the imports. If you display something, it will show. You can see it's still retaining it here. All of these things, I don't need to run them. So this is readable. You can see the plots that we made that are just shown there, right? You can see all of this information. They're all there. You can see the plots again. You can see them. You can also see after doing the models, you can also see the whole plot that generated the images and the statistics. So this is what you need to do. I'm not saying you should follow my style. I'm not saying you should do machine learning. You don't have to do machine learning. What you need to do is to just write your whole concept the same way it was described here. Write your whole concept, title and objective, your description, do your analytics, do your whole data cleaning and processing, or what we call the exploratory data analysis. Do your modeling or analysis. So remember, you must not exactly follow this. Just choose the one that is applicable to you. Discuss your result and interpretation, and just table by table. So notebook or notebooks allow you to do write text and also do your code that can be displayed that anyone can see. So just like what we have here. If somebody is going this right now, they don't even need to run this. They all just need to do is to read through these notebooks. You understand? And they're able to understand what has happened, the whole process from beginning to end. So that is what we are appealing to you to do. That's what we're advising you to do. So you don't have to go. I know many of you are already used to doing a presentation. You can do, if you want, you can do the presentation, PPT or whatever, and keep it somewhere. Maybe in your colloquium, you can also say, oh, in the course of doing this. Or if you want, you can also do it, keep it for yourself. And then maybe if you're applying for any opportunity, you can also add it. Or maybe if you are applying for opportunity, you can also add it as part of your project. Share your code, and then maybe also add the PPT in your GitHub repo to show people that, oh, this is what you did. So, but for us, we don't need that. For time constraints, we don't need it. We need to see that want to see how you're able to do this in a notebook that somebody can read and infer exactly what you have done. So take the process from the title down to the conclusion and references. That is what we want to see. I'm not sure if there's any other question, but I know people have been asking these questions. A number of you are DMing, sending private messages, and I don't think it is wise because we've been answering this over and over again. So that's all, guys. I think this is actually the end of this whole lecture thing. Yeah. You're going to wait for subsequent email from us. I think we'll have a quick chat next week around the same time to discuss, maybe based on the whole project that we have received, how you can improve on them, and then if there are any other questions, some next steps that you might want to consider. I know BRICS Hackathon will come sometime later this year or next year. So BRICS Data Science or either data science or machine learning hackathon. So you need to look out for this. Again, that we are lending our lecture doesn't mean that your training have ended. If you know you have not consumed the resources, go and continue consuming them. Keep them to yourself. They might not be useful for you today in your academic exercise, but they might be very useful for you tomorrow. So this information, don't just leave it there. If you have not been programming before, okay, yeah, so you've seen the message, the hackathon will be this year around September. So please look out for the hackathon. And be rest assured the information will be shared in the Slack. Okay. Please look out for it. So you need to keep developing your skills so that you'll be able to use it during the hackathon. Somebody's saying, when does BRICS Science Communication Training Program take place? I'm not sure I'm in a better position to answer this question. Narusha, not sure if you're there, you can also respond. I'm not aware of that information. Yeah, so guys, I think we'll stop here. And any subsequent questions, please put it in Slack. Please just add it in the Slack channel. And if you have any information that you want to share with us, do also share it in the Slack group. So thank you very much for joining us for this program. We look forward to hearing from you. We are still looking forward to your project submission. And for those who submitted, like we said, we're going to evaluate it. You're going to get feedback on maybe things that you need to improve on. and all that, and also, if you meet the requirement for certificates, you also get a certificate. And again, what we said, let this lesson, please let it not end here. If you know you have not still mastered your programming skill, take your time later, keep refining it by getting your hands dirty. I know this 8 weeks is too short to run all of these things from beginning to end, but it's already giving you an overview. And if you are the type that still uses Excel or some other softwares to do your analysis, you're already seeing that there's an opportunity to do this in Python. So please get started. It is not late, okay? Get started. That's the only way you start. Take your data, try and load it in Python, try and do analysis with it, try and do some data inspection, try and clean the data sets if need be. Google is your friend. You can always search on Google to see how to do some feature engineering, how to do some data cleaning. Many of them were already shared in the notebooks as additional resources for you, but don't limit yourself to that information. You can also search online. You'll see more information. Try and do plots, different kind of plots. Try Seaborn, try even Plotly. There are even newer packages now. Try, for those who are not in astronomy, um, I would also advise you to search for Python packages for your field and see how the common package that is applicable to your field, whether it is economics, whether it is engineering, whether it is finance, whether it is biological science, whether it is social science. You are going to find chunk of Python packages that is applicable to your field. So don't all restrict yourself to the ones that were used in this course, but be rest assured that the information that you need, like the foundation course information, have been shared with you already. The whole common packages for doing data analysis have been, you've already used them. So you're already getting started with them, but there are still tons of them out there. So, okay, on this note, thank you for joining us this evening. We look forward to your submissions. Do have a great evening. Bye, everyone.
Thank you, sir.